Hello, good morning, everyone. Welcome to day number 3 of this PhD level course on, let me just share my screen here. There you go, and go to Canvas. To our course. What is the title of our course, by the way? Advanced Modeling of DER-Rich Active Distribution Networks. This is the view that you have as students of Canvas. Right now, you have gone through days 1 and days 2, and now we're in day 3. We're going to have 4 blocks as before, and as the whole course is going to continue. Today, we're going to talk about orchestration of distributed resources and active distribution networks. So it sounds very similar to what has been said before, but as I said in my welcome video, the whole idea today really is to have more of an engineering flavor to things. And as much as I've been using as a student myself, the OPF as a researcher, as an academic, and many people in my team as well use the OPF. The reality is that the OPF is far from being applicable to industry. Is making a lot of progress, but there are many challenges. So I think that there's future and there's a massive role for it, but we need to understand those challenges. So I want to really get a little bit more into those challenges, understanding the context in which OPF can be used, and also discussing the different aspects that we need to address to really make it as a tool, to see it as a tool in the industry in the years to come. So how I divided this day was first just to discuss those challenges, as I mentioned. So that's what we're going to do in this first 45, 50 minutes. Then we're going to get into, well, OPF and DR rich distribution network, which is just another title. It sounds very similar to everything. But the idea there is that we're going to talk about a little bit more about hosting capacity, some examples using the OPF for planning purposes. And then we're going to get into a little piece of code that we made it available to our students here a few years ago, and then we're making it available to you guys. You need to download a platform called AIMS. There's an academic license, a free academic license, or free license anyways. So you just need to put there and then that you're a student or whatever. And the information is there on Canvas. And then we're going to move into 3-phase OPF lessons learned from large-scale realistic implementations. So it's very interesting, to see that there are a lot of formulations, there's a lot of work around the world about OPF, but the reality is that distribution networks are 3-phase, right? Distribution networks can have very complex elements or complex parts. And at the very end of the day, if you really want to deal with distributed resources, well, yes, there are solar farms, there are wind farms, but the large majority, when we talk about electric vehicles, we talk about rooftop solar photovoltaic panels, residential batteries, we're talking about houses. Houses are connected as single phase elements to the network. So if you cannot model the OPF as a 3-phase network, well, you are gonna end up having some compromises that are needed sometimes, all right? But we need to understand, those compromises. And if you want to really model things into very, very detailed, well, I mean, that's what we're gonna discuss a little bit of what are advantages. And then we're gonna finalize the day with DER and network integrity, meter level operating envelopes. I saw there was one question, I think it was yesterday, about operating envelopes and OPF. Well, there you go. That's your answer for that person that asked, and we will discuss all those aspects. All right, so let's start today. All the slides for block 1 are there. Also, the slide for block 2. Then I will, during the break, I will upload the slide for block 3 and 4. There's a lot of links there to different papers that we have, YouTube videos, etc., etc. So please feel free to explore that content. So let's start with block 1 here. And there you go. So that's us. One thing that I would like to do today is to allow the interaction of questions, with the audience in real time rather than waiting for the whole thing. So rather than making a presentation where you guys have to listen the whole thing, feel free to make your questions, and we'll check there not the chat room. Do not use the chat room. There's a question and answer bit there, so use that. I will answer them in real time. However, we will also, if you want to speak your question, you have a microphone. So just raise your hand, and we will allow you to speak. So introduce yourself, your name, your affiliation, where you're from, and just make the question, and then I will answer this. So feel free to interrupt me. There's nothing wrong with that, and we have time for that. Okay, so we are going to have both the Q&A as written, and we're going to have as well the ability for you guys to speak as well. But raise your hand. Okay, so let's continue. So let's start with block 1. So what I'm going to go through is really give you a bit of context. You know, what were we talking about distributed energy resources? What is the evolution of distribution networks? Are distribution networks so advanced that we need OPF today? Well, not really. Actually, distribution networks are perhaps the dumbest part of the whole electricity system. The advanced part has always been the transmission, that, you know, of course, manages the generation, the bulk generation. The thing is that distribution networks now are having much more than just loads. The networks are already struggling with all the technologies that are being connected to it, particularly at the very low voltage levels. And this is pushing an evolution, all right? And we're going to discuss a little bit about that. And that's why now all the smartness has to go to distribution. We're going to discuss about the impacts of distributed resources. It's very, let's say, easy to dwell a little bit too much into the mathematics of OPF and forgetting about the engineering aspects. So we're going to talk about engineering today a lot. So there's no point in trying to implement an OPF to maximize the installed capacity of photovoltaic farms when we don't understand what are the problems that a photovoltaic farm might bring to a distribution network. So let's discuss that. Same thing with electric vehicles or whatever technology, all right? So we're going to discuss the impacts, the solutions at a high level, and also hosting capacity, which is a term that we're going to use every now and then throughout my slides, not just in this block, but in other blocks. Then we're going to get into optimal power flow in distribution. So what is the idea of using optimal power flow for operation? And what is the idea of using optimal power flow for planning? Those are different things, all right? And might still be using potentially an OPF formulation, but the aims are different and the challenges are different as well. And talking about the challenges, as I mentioned earlier, there are lots of challenges when it comes to implementing any optimal power flow. You can argue that it's the same challenge as just running a power flow to start with. To run a power flow, you need a network, correct? So surprise, surprise, distribution companies around the world do not have necessarily all their electric models either complete in all the voltage levels, particularly the lowest ones. And sometimes they are not really that great. They are not that accurate. So they might have the geographical information system in a very, very good way. So topologically wise, you know, the coordinates, what perhaps type of conductor to some extent. And of course, they know their customers, but they don't necessarily know what is a phase grouping. They don't necessarily know where that and that customer is really connected to that and that transformer sometimes. Sometimes they do not know exactly what type of conductor it is, and then that means how can you calculate the impedances. So there are many challenges there when it comes to the modeling aspects, and there are challenges as well modeling the distributed energy resources. So the OPF is just part of a massive, you know, process by which we are trying to create smart processes for decision-making purposes. Okay. Now, just to put a little bit of let's say a silver lining to all these challenges, I will show some discussions, you know, of what we need to do, you know, to move towards real implementations, you know, and finalize with a little bit of comments on hardware in the loop. So this can be done, all right? So there are many challenges. I'm trying to say that the OPF is useless, not at all, but we need to be very aware of all those challenges. Okay, so if you have any questions, well, you have the Q&A there, and of course, raise your hand as needed. Okay, so what is the context of all these at the end of the day? So we have distributed energy resources around the world, and it is increasing, particularly, of course, in developed nations. Why? Because the cost has dropped in the last decade so much that it is cost-effective, certain technologies, to many countries. Not everywhere in the world, that's true, but the cost declines are so big that now people can afford it. Here in Australia, for instance, almost 1 in 4 houses have a solar rooftop photovoltaic system. And by the end of 2019, I think that 2020 perhaps as well, Australia was having a third, more or less, of the market share of residential batteries in the world, which is quite impressive as well. So, or at least was estimated. So that's the context. Technology is getting cheaper, and therefore is more accessible. It will be more accessible first to developed nations, of course, rich nations, and then eventually, as the market grows, they will be cheaper and cheaper and cheaper to everyone. Now, as I mentioned, Australia right now, in terms of photovoltaics, has almost 1 in 4 houses. That's one of the largest penetrations of rooftop solar photovoltaics in the world. Now, of course, as a nation, there's a number of houses. It's tiny compared to many other countries, but still it's quite significant. So the peak demand right now of the national electricity market, which is pretty, yeah, it is, because we don't have, Australia is pretty big. We don't have the western part and the eastern part connected, so they are separated. So NEM stands for the national electricity market, but it's actually just the eastern part, and that is around 36 gigawatts, the peak demand. Right now we have, well, that number should have already perhaps reached 20 gigawatts of installed capacity photovoltaics. And that's not just residential photovoltaic, that's residential, commercial, and of course, solar photovoltaic farms. That's quite a lot, guys. And that means that we are already seeing a lot of challenges at the distribution level, because everything that is photovoltaics is connected at distribution. There's nothing connected at transmission levels, right? So that is significant, because when people are not at home, when businesses are not turning their whatever it is loads on, all the generation continues to flow, and that means reverse power flows and some challenges there that we're going to discuss in this blog. Now, in terms of residential batteries, we should have already surpassed the 100K mark. That is tiny, of course. If we are looking at right now having almost I don't know, more than 2 million houses already with solar photovoltaics, and 100,000 only with batteries, that's very tiny, correct? But as tiny as it is still a quite impressive number relative to what we have in terms of solar photovoltaics when you compare it to the rest of the world, all right? So that is the context that says, well, I think distributed energy resources are happening, not just in Australia, it's actually happening in many parts of the world, and not just developed nations, in developing nations as well. So this chart here is from Bloomberg. Already it's a little bit old, but it's still, it's very, very useful to reflect on how things are evolving. Now, this is the centralization ratio of electricity generation. And yeah, Australia in dark blue there going on top. That's interesting. That's exciting, because we're talking about here about low carbon technologies, the decarbonization of electricity, and that's all fantastic. However, of course, that brings a lot of challenges. Distributed energy resources are connected to the distribution network. The distribution network was designed for peak demand, and that's it. All right, that's how we have done things for decades, and it has worked beautifully. It works. The moment that you have other type of technologies that actually generate, and even electric vehicles that are more demand, well, I mean, if they are connected to a network that were designed just for normal demand, then you're going to have significant challenges. So that's why we're moving, to first understand those impacts, and they are already happening in many countries, and then to integrate. So we're moving to integrate distributed energy resources, which is essentially, okay, how can we fix things as soon as possible? That's where, standards come in, volt functions, volt-var functions, for photovoltaic systems, level 1, level 2 charging, which is essentially limiting, the amount of power that you can withdraw, for a charging point, with your electric vehicle. And that's all good, but that's not enough. That's not being necessarily a clever system that can really do things actively. We need those solutions, of course, because the uptake of the technologies is quite high in many countries. And well, by the time that you start really defining, how it's going to look your smart grid, it already took years. So you need solutions, but eventually we need to move to what we call DER orchestration, which is really smart grids. It's really the more or the most effective way of managing distributed energy resources and the networks themselves. Now, that's not to say that all the time we need to think of the orchestration as a solution. You need to compare it to planning alternatives that are traditional as well, like putting bigger cables, bigger transformers, because at the end of the day, this is about money, all right? So if smart grids are more expensive in the long run than just doing traditional reinforcements or network augmentation, as it's also called, well, you go for network augmentation. That's pretty obvious, all right? Anyways, so in terms of the evolution of distribution networks, what we are seeing that has happened and is happening as well in different kind of paces around the world is that we have moved already in many countries from what I can call passive networks. So this is what we used to do normally, be business as usual, right? So you design your network for the peak load, all right? So we're talking about distribution. And if there's any new technology, particularly, perhaps, 20 years ago, a wind farm coming, a random wind farm, now it's not random anymore. You would say, all right, how big is your wind farm? Okay, so you can connect it here. Let me check the minimum demand. Okay, so your maximum generation, no, you cannot connect more than this X amount of megawatts. That's it. Thank you very much, mate. You want to connect to much more and you create impacts. Oh, here's your bill, to upgrade the network. So that's what we've been doing actually many years ago, because again, distribution networks were not designed to host these new technologies. Therefore, they were headaches. That's what they were for distribution engineers. So that's what we call fit and forget. All right. So you make the calculations of what you can connect as your wind farm, 2 decades ago, and you tell the corresponding investor, well, this is your maximum. If you're going to connect more, well, you need to pay for the upgrades or some part of the upgrades, and that's it. The idea is that once you fit that wind farm, you forget about it. You don't need to control anything because it just works for the maximum generation and minimum demand, so for the worst case scenario. Now, in the last few decades as well, in parallel, we haven't seen just wind farms connecting randomly. What we have seen as well is a lot of distribution automation, and this is totally driven by reliability. So this is about having very intelligent systems that detect faults and take an action, like for instance, automatic reconfiguration or remote reconfiguration. Not necessarily automatic, semi-automatic perhaps. And this has happening because reliability is one of the very important metrics that we use to regulate, penalize, or incentivize distribution companies around the world, where they are natural monopolies, of course, and then therefore we need to make them, be efficient with some metrics. And because of that, that metric has been very important around the world. They have been investing in distribution automation. But in terms of distributing their resources, again, 20 years ago, whatever, they have been treated the same way. So fit and forget. However, in the last decade, we have seen the rise of distributed energy resources. And with this rise of distributed energy resources, what I call moderate DER, I'd say moderate because we don't have lots of it, right? So perhaps some pockets in certain countries, but in general, it's not lots of it, all right? As much as I say 1 in 4 houses in Australia, that's not lots, that's 25%, all right? There are networks, of course, there are pockets, neighborhoods in Australia where you really have much more than that, right? Because people start saying, well, the neighbor has it, the neighbor is solid, whatever. But in general, it's not, you can call it moderate. So in this context, that's where we are right now, in the moderate distributed energy resources kind of scenario. Things are getting a little bit more interesting. So we are integrating distributed energy resources. But this integration is really being done by exploiting distributed energy resources themselves. So we're doing this for distributed energy resources to solve their own issues. Again, as I was mentioning earlier, solar photovoltaics with standards that check the voltage at the connection point and reduce the watts. So that's the volt-watt function of photovoltaics. Or when we are talking about electric vehicles, well, you just have level 1 or level 2 charges, which is approximately what, 10 to 15 amps to 30 amps for level 2. And that what it is saying is, well, we are not going to control right now distributed resources too complex, but we're going to limit, or if we can impose certain standards, we're going to make them do things to help a little bit with network operation. And then, is there anything wrong with this? There's nothing wrong with this. We need to do it. We need to do it because the uptake of DER is going really, really fast, depending on the technology, depending on the part of the world that you are. So that is important. However, that is not active management proper. I mean, it's semi-active management to some extent, if you want. There's the exploration of using already in different countries, for instance, checking what is happening downstream your medium voltage feeders, and the end customers, what is the voltage, and then playing with your own local changers, for instance. And that's a little bit of active network management. So they're incorporating this. They're incorporating the use of settings to some extent, for wind farms and solar farms. But it's really, really limited in terms of examples. It's not business as usual yet in terms of really proper active networks. But I put it as active network because it's kind of the beginning there, right? What we want really at the end, okay, we want these super duper active networks, right? We want the smart grids, and that's orchestration, right? So that's why I try to differentiate integration from orchestration, right? Integration allows us to have all the standard different things, constraints, if you want, to have more DER, but eventually you want to orchestrate it. You want to actively manage all the different participants in the network and the network itself as well, because the network has controllable elements. And what we want to achieve with this is just the best use possible and control of distributed energy resources and network assets to do many, many interesting things. Okay, there's a question here from Sarah. In the DER orchestration stage, what time scales and time ranges do you see that are required for operations such as volt var, demand response, etc.? Well, volt var, so you're talking about orchestration as in managing all the different things. The time scale depends on what are your different applications, Sarah. So for instance, typically if the standard, for voltage constraints, right, in a distribution network here in Australia is monitoring every minute the voltages. Okay, it's not that they are monitoring the voltage all the time, but if you really want to check the standard, it says that every minute we need to be within the limits. All right. If you look at other standards around the world, it will be every 10 minutes. In America, for instance, is instantaneous almost. So it depends on the standard, on the requirements of you're in the world, right? So if my requirements, in my part of the world says every 10 minutes my voltage has to be within this limit, so my control cycle then will have perhaps to be just a little bit less than 10 minutes, right? Certainly no more than that, because I might not hit the target. So it really depends on that. So it's not that everything has to be done every second or everything has to be done every 5 minutes. It depends on how things are assessed in each country because of the different local requirements, okay? And also depends in terms of what you're trying to extract. So orchestration is about, again, smart grids, the bigger kind of terminology. And if orchestration is not just to manage voltages, as I just discussed, it's also to manage, for instance, the provision of services, let's say batteries and aggregators, are trying to move flows. We're going to discuss this in block 4. Are trying to inject power because the whole system, the system operator needs a lot of power at a given moment in time, energy. So if this needs to be done in 5 minutes, it means that your control cycle has to be at least 5 minutes. But if this needs to be done every 10 or 20 minutes, then again, your control cycle might be a little bit longer. So it all depends on what you're trying to achieve. There's no single answer here. Now, there's a question from David. Should the standards for how often voltage is checked change with large DR generation percentage? Well, David, that's a very good question. There are two issues here. So how often the voltage, for instance, for the volt watt and the volt var is being checked is one thing. But another is, and I think is more important, is that these standards, the moment that their evolution, the big problem with the standards is that they are being defined literally with specific values and settings all over the world, all right? So you have the IEEE, different IEEE versions, for instance, for the inverters, photovoltaics, and then you have a standard for many other things, right? But they are being defined explicitly with settings, all right? And then each country as well has their own adaptations, but with the specific settings, values that are, of course, relative to the conditions of each country. However, the problem with the standards is, or let's say the challenge, is that those values that have been defined might be very good for the next 5 years, but then suddenly there's an uptake that wasn't foreseen, and then, well, that standard becomes useless because it will not solve the problems. So it's not really about how often the voltage is being checked. That is not that relevant because the standards are pretty good on solving that. But the problems are the specific settings. When you say, well, no, actually, for my volt watt, it is at the 250 volts. By the way, the maximum voltage at the phase 2 neutral here in Australia at the residential level should be 253 volts. That's 10% above 230 volts line to neutral. And so if my standard is saying that at 250, I need to start curtailing, well, that might be very conservative, but if it says, no, at 255, I need to start curtailing, perhaps that is okay today, but in 10 years, it might not be good. So the challenge with the standards is that the moment that we have specific settings, they become obsolete or not adequate, the more DER we have. There's another question here. Concerning the increasing DER in Australian distribution network, what kind of critical challenges foresee with impact distribution network, which is not addressed at the moment? Well, all the challenges. Do you think that voltages are perfect here in Australia right now? Nowhere in the world, by the way. So we're going to discuss that. But eventually, it's orchestration that the one that is a big challenge as well. Then Sari is working on an IEEE standard, Margaret and Richard. Okay, recommendation for aggregators. Yeah, that's interesting, Sarah. Thank you. All right, let's moving on. So what we want to achieve eventually, is a smart and low carbon system, all right? So of course, this is a course in distribution, and I'm a distribution person. So of course, all the smarts are in distribution according to me, but there's a lot of smarts in transmission as well. So what we are going to see in the future is, and we're seeing already in many countries, is medium scale controllable distributed resources. So not just the solar farms or wind farms, but also storage as well. And this is happening quite rapidly, which is exciting. We are also going to see more hierarchical control, the substations or local control closer to the end customers, the transformers. We're going to see much more scalable, small scale controllable distributed resources, so at home, and more advanced network management, and eventually perhaps as well distribution helping transmission, and well, to provide services on the energy market, frequency response, and the operation of the transmission system. Why not? Why cannot distribution help the whole operation of the system? And that can actually happen, and it is happening actually, by the way. Let's start now discussing the basics. All right, so that's the big context. There was a hand up, I think, guys. I don't know. Well, Arthur, Carmen, just keep a look at that, and it's just allowed to speak.
Yeah, I did that, and yeah, I think they gave up to ask the question. I don't know why.
All right, okay. So let's move on. So that was the big context, guys. So let's start with the basics. All right. So we're engineers. Okay, most of you perhaps. I am an engineer, so I like to enter the engineering part. So when we look at a low voltage network, so this is like, for instance, 400 volts line to line here in Australia and 230 volts line to neutral. That's similar as well in Europe and other parts of the world. So what we do is we consider what we call the after diversity maximum demand, or the average peak, if you want, of a house. For instance, here in Australia, depending on the part of Australia that you are, the socioeconomics, it can be around 4 kilowatts. Sounds quite high, is because air conditioners. So 4 kilowatts, and then you have 6 houses here, so 4 multiplied by 6, that's 24. You put a little bit of an engineering factor there, perhaps 6 kilowatts more, and then that's 30 kilowatts. So of course there's reactive power and other things, and so you end up with a transformer that is the next highest, right? So let's suppose it's a 40 kVA transformer, and then that's it. That's how you design the transformer. And then the cables, perhaps it will be, depending on the part of Australia that you are, no more than, I don't know, whatever, depending on the number of houses there and the spacing that you do per house. Perhaps it will be, I don't know, 200 meters, 100 meters. I mean, 6 houses must be 100 meters, just a street. And then you did size the corresponding conductors and everything. Why? Everything is done. So you have assets that are not congested, and you have voltages that are always within the statutory limits. That's how we do it everywhere in the world, with different ADMD values, of course. The challenge is that you design that low voltage network, and then suddenly people are having photovoltaics. The thing with photovoltaics is that the sun shines to everyone simultaneously. And then that means that when no one is at home, then all these photovoltaic panels can create reverse power flows, because of course, your fridge might be using electricity, but it's super, super tiny and it's cyclic anyways. So if everyone decided to install panels, I don't know, let's put a value there, all right? A crazy value that is not real, all right? Just because of the scale of this little example, everyone puts, I don't know, a 10 kilowatt system. So 10 multiplied by 4, that's 40, and then 40 might be exceeding, the limits, the thermal limits of the elements that we use to design this network. And of course, there will be a voltage rise as well, okay? Now, these problems are happening around the world, where we are seeing more and more uptake of photovoltaics. And it's not just in the low voltage. Of course, the moment that you look at many neighborhoods doing the same, you are going to have the same reverse power flows, and you are going to affect as well the corresponding voltages and flows on the medium voltage size, for instance, the 22 kilovolt line to line. Now, in reality, well, you have still commercial customers, you have industrial customers, and then they are going to take that electricity that is being generated. But still, it can reach a point where you actually have reverse power flows that go up to the sub-transmission part, right? And this is happening. This is not nothing like crazy. This is already happening in different parts of the world, right? So the question is then, how can we determine the hosting capacity of our networks? How can we know what is the limit? And then, well, at least we can stop there to avoid problems, right? And then, of course, once you know the hosting capacity, then what is the best way to increase that hosting capacity? How can I actually make sure that we can have more than, I don't know, 30% of the houses with photovoltaics? I can have more, because obviously we want to help people installing or being able to install this. We want to facilitate this technology to be used, all right? Now, you can do many things, as I was mentioning, as the year integration. You can control inverters, perhaps locally through standards, but you can do perhaps something a little bit more clever as well. So you can actually control actively what is happening with the inverter in terms of, the export that is happening there at the different times, sending signals when needed. So we could potentially think of a future where we actually actively say, well, do this. It's not just curtailing, or limiting the active power that is being injected, but also, for instance, the reactive power. Or what if we just give different settings for the volt watt and volt bar functions, So there are many things that can be done, all right? Why are we always thinking about inverters? Why cannot we just change the taps of the on-load changer in the primary substation? Well, we can do that as well, So what about storage? Well, the moment that you install the storage, why cannot we have a process by which storage could also help the network? This is something I'm not going to present today, but actually, as a matter of fact, if you buy a battery today, the battery is going to be awesome for you as an end user, but for the network, it's not great, because the batteries get full very, very quickly when they are in self-consumption mode, meaning they absorb everything that they can as soon as there are reverse power flows, and then they get full in the day, all right? And that means that we still have reverse power flows. There's a lot of documentation that I have on that. But still, the battery is a very flexible technology. We could send commands, for them to do something a little bit clever. So there are opportunities. Let's talk about electric vehicles. Same thing as with photovoltaics. It's a new technology, and the moment that we have electric vehicles, many projects which have been involved as well are showing us that well, there's a coincidence, all right? It's not a coincidence like 80%, or like super high like photovoltaics, but there's a coincidence when people actually come back from work and actually charge simultaneously. So that coincidence means that we're going to have an excess of demand when people come back from home, which also happens to be a peak demand in many countries. And then therefore, it means that we are going to have a higher peak demand that the network has been designed for. And that means, of course, voltage drops and congestions. And that is a challenge, of course. Now, what is the challenge for medium voltage networks? Same thing, because it's more demand, we're going to have problems as well, thermal and voltage problems. And then the same question comes back. How can we determine the hosting capacity of our networks, and what is the best way to increase that hosting capacity? I'm going to stop, because there are some questions here. Okay, no, there's no question here. All right. Now, can we manage electric vehicles? Yes, we can manage electric vehicles. Of course, we can manage electric vehicles. We can manage the charging point of the electric vehicle, or we can send commands to the electric vehicle. And with that, we can actually perhaps avoid those problems. That means, of course, when we were talking about photovoltaics, we might need to reduce the injection of power. In this case, we need to reduce the absorption of power, active power. Now, that has implications, both of them, all right? And we need to consider what is the effects on end customer. So it's not about just doing something clever for the grid, it's also something clever for the end customer. Because at the end of the day, that customer that we're talking about is the customer of the company that is managing the poles and wires. It's us, all right? So we cannot forget about that, right? But we can do it, technically speaking, yes, we can. And there are projects around the world that are showing this, So there's a potential to do things there. All right, so yeah, distribution networks are evolving. Yes, there are impacts from distributed resources, and there are potential solutions. So let's get into just some definitions around hosting capacity, so we're on the same page. So when I'm talking about hosting capacity here, I'm referring to the maximum amount of distributed energy resources that a given distribution network or part of it can host without negatively affecting its normal operation at any point in time. Now, what do I mean by normal operation? So it will depend on whoever is doing the assessment. So normally I will refer to these to voltage at limits. So for instance, in the low voltage here in Australia, plus 10% of the nominal, minus 6% of the nominal. Asset utilization, so the thermal capacity, of your assets, typically referred to depending on the critical season of the year. So here in Australia is summer. But it can be also normal operation with respect to fault levels, to harmonics, and many other things, right? It's not just voltages and asset utilization. When I refer to the amount of DDR, it's really what people, and I will use a lot as well, as distributed energy resource penetration. So it could be EV penetration or PV penetration, but this can be defined in many ways. It can be the number of distributed energy resources, as devices in the corresponding network they are assessing. It can be the percentage of customers with that technology. It can be the kilowatts of the total DR capacity. It can be many things. So that needs to be defined as well. And when I refer to solutions, I will refer to traditional and non-traditional solutions as well. So traditional for me, or implementable, are solutions that distribution companies use or can use, let's say, now, today, without significant complexity. Whereas non-traditional are those solutions that they could use, again, of course, to increase hosting capacity, but perhaps with some complexity, all right? So the moment that we talk about active control, and all the context of OPF, that we're going to go back to this, is really about active control or planning with more futuristic, controls. Those are futuristic, unfortunately, to some extent. And then therefore, if it's futuristic and it requires still some other type of infrastructure to be implemented, then that is naturally non-traditional. Eventually, it might become traditional because that's what we do normally, but today it's not. So let's discuss a little bit more about these traditional and non-traditional solutions to increase distributed energy resources or the hosting capacity, for us to be able to have more of these technologies. So in terms of traditional, obviously, increasing the sizes of our wires and our transformers. So this is network augmentation. In America, it's called wires alternatives, all right? Well, it's not just the wires, it's transformers as well. So that's why I don't like wires alternatives. Anyways, it's also called reinforcement in some other parts of the world, all right? And that's pretty obvious, all right? It is time consuming, it's expensive, of course, but any other thing that you can come up with is going to be expensive anyways. So you can actually use as well better settings for your offload tap changers. So these are the distribution transformers. Some of them in some countries can actually be disconnected. So that's why it's off. And then you just move the tap. You don't have many positions. By doing that, you can actually regulate the voltage and then bring benefits, either because of excess of load or because of excess of generation. You can have better settings in your on-load tap changers in the primary subs as well. And you can, of course, implement, and I call it traditional now because these are standards and we're using them around the world, you can implement the standards, that involve the volt watt functionality for photovoltaics or volt var, impose your level 1 or level 2 charging, etc. So this is kind of restricting things, all right? So distribution companies are doing this in many countries or will be doing this in many countries. And then we have the non-traditional ones, which of course, as you can see here, is active control, all right? So these are the sort of solutions that distribution companies are exploring or will be exploring as well, right? So again, it depends on the context of the world that you are in. When I say active control, that doesn't mean that it's all a centralized entity, sending commands. It can be all local as well, but in a more advanced way, different from what we're doing today. And this can be, for instance, you have a sensor in your critical customers, and then that sensor sends information to your on-load tab changer at the primary sub, and then, well, you just change the tabs, your on-load tabs, accordingly, according to the voltages that you want to achieve. There can be other type of sensors and other type of logics. You could install low voltage on-load tab changers. They're quite expensive, but they are a very flexible technology. And again, control them according to the voltages that you are sensing. You can control actively distributed resources, as I was mentioning earlier. We can send settings to the photovoltaic inverters, to the inverters of the batteries, to the charging points of the cars, or to the cars themselves. This is being explored, all right? And this will continue to be explored because we need to understand what are the advantages, what are the complications, and what is the cost, because at the end of the day, we need to compare them. This is not about going non-traditional or going full-blown with active control. This is about finding what is the most cost-effective, right? It is never about doing the clever thing, technically speaking. This is about doing the clever thing from a cost-effective perspective, right? So the question is, which are the most cost-effective solutions? That's what it is about. Now, the thing is that, unfortunately, when you look at these solutions, they do not necessarily solve all the problems, right? So there's no single solution. So what you are going to have is the augmentation. It will solve current problems, meaning like the congestion problems, because of course it's a bigger asset. But voltage problems, not necessarily. Yes, you can argue, well, Nando, it's you have larger cross sections of conductors, and then it's lower impedance, and that can help. That's true. But the extent to which it can help, it depends, because it's not necessarily a massive jump in terms of the change of impedance when you change from one conductor to another size, all right? What if you actually play with off-load tab changers? Well, it changes the voltages, but it doesn't change what is happening with the current significantly. Yes, there is an effect of voltage changes and the load, because our loads are, a mix of impedance, constant current, constant power, but still, it's really the voltages. On-load tab changers in the primary sub is voltages, it's not asset congestion. What about the DR settings or limits? Well, I mean, sometimes it might be voltages, sometimes it might be currents. So it really depends on what it is. That should have been another question mark for voltages. What about non-traditional? Well, again, same thing, you want to control actively your on-load tab changers in the medium voltage, in the low voltage. Well, that's voltage only. What about acid congestion? And if you want to control your DER, well, you can control voltage, but what about acid congestion as well? So there's no silver bullet. That's the main thing here. So we need to look at solutions in a way where we need to mix the different benefits from individual solutions, all right? And also it depends on the problem. If you have a rural network, certain solutions are more appropriate than what you would use in an urban network. Why? Because a rural network is much, much larger, less customers, but the impedances are massive, and then therefore voltage are much more sensitive, to whatever new technology you're going to put. So it really depends on the different problems that you're going to find in the different types of networks, and also depends on the expected uptake of DER. If you're really expecting that in the next 5 years you're going to have all your houses with photovoltaics, it's very different that you will never have more than 40% in a given area. So what is the value? So depending on that, on the penetration that you're expecting, because in reality, not all houses can have photovoltaics. Why? Because they don't have the roof for that, right? As simple as that. Or in some cases, not all houses are going to have electric vehicles. Why? Because they don't have a parking space or whatever it is. They are made not to use, cars, whatever it is, there will always be restrictions. So therefore, if we knew what is the potential uptake, also we can decide what is the best solution. So it's not that simple, right? So therefore, the question really is, which is the most cost-effective mix of solutions for a given distributed energy resource penetration and type of network, right? Now, at this stage, some of you might be, okay, Nando, that's very interesting. But, what about OPF? Okay, so let's go back to the OPF, all right? So what is the role of OPF in distribution? Now, for me, the ACOPF, all right, is just a tool. Okay, it's not a tool per se, it's a formulation of a problem, but it's a very powerful one, all right? Now, we can use it for operation purposes, or we can use it for planning purposes. Now, now that you understand a little bit, the challenges of distributed resources and the potential control opportunities, at a high level, now we can think of two streams of work with the OPF. We can think of this as operation, really sending settings that you need to calculate every time, every 1 minute, every 5 minutes, 10 minutes, half an hour, depending, again, on the characteristics of how you measure issues, okay? As I was mentioning to one of the questions earlier. These settings are not just to calculate what is the photovoltaic inverter going to do or where my charging point should be disconnected or not. This is also involving, perhaps, if I have that opportunity, connecting or disconnecting a capacitor bank, or changing the position of the on-load changer of the controllable elements I have on the network side, right? So whatever it is, all this range of settings is to ensure network integrity. So what are the right settings that make it possible that voltages are within limits, that my assets are not being congested? It can be incorporating other things like fault levels, harmonics, etc., whatever you want, all right? And all of this, of course, looking at an objective, and we're going to discuss that in the next few slides as well. There has to be an objective, of course. Now, for instance, what would be the example of this? Dynamic export limits, photovoltaics every 5 minutes, or this disconnection or scheduling of electric vehicles, you can do it every number of minutes, changing the capacitor banks on the OLTCs, etc. So that's operation. So that means that we need something that is fast, right? Now, another aspect of how you can use the OPF is planning. Now, when it comes to planning, we're talking about hosting capacity. So it's to answer a totally different question. So on the operation, we are trying to come up with settings, right? When you look at the OPF for planning purposes, is to answer another different type of question, which is, what would be the largest wind farm that I can install here, for instance? That's hosting capacity, right? If we're looking at multiple positions of wind farms or solar farms or electric vehicles, depending on what you're modeling, now I can use my OPF to answer another type of question, a planning question. And of course, in this case, we're looking at, if it is planning, we can always look at the critical worst case scenario, well, worst case scenario is critical by definition. For instance, like if we're looking at generation, would be the maximum generation and minimum demand. So for instance, if we're looking at a solar PV farm, it would be, at midday, all right? So what is the demand? And then you just optimize, your problem, and then you find how much you can inject. And then that's it, worst case scenario. But if you really want to do it for planning purposes properly, you want to explore what is happening across weeks or years, all right? So you can actually capture, the different interactions of demand and generation. Not only that, you can embed operation into planning, and then you can really sort of assess that hosting capacity, considering the potential smartness that you might have in the future. And then, well, you can see, how hosting capacity can actually evolve with different smarts. So this is about optimal location and size of distributed resources, optimal network upgrades. It's not just hosting capacity, it can involve upgrades as well, many things. But the timescales are very different, which means also, of course, their applications or their formulations are going to be different, right? With operation, you want to be precise and fast. With planning, you don't need to be that precise because it's to inform planning, all right? And because the problem is going to be so big that, well, you need to do some compromises. So the OPF can have a massive role in the operation and planning of distributed energy resources or DER-rich distribution networks. At the same time, there are many challenges for it to be adopted by industry. And we are going to discuss them. All right, moving on. So some of the basics of OPF. So you have gone through day 1 and day 2 with Steven, and he is great. And definitely you have been through all the different formulations. So I'm not going to spend a lot of time on this, but what I want to highlight here is that, well, the basis of OPF is that you are going to have an objective function. It's either maximizing or minimizing, all right? Whether it is for operation or planning doesn't matter. The basis of an OPF, for distribution, if we look at, of a single phase or a balanced distribution of OPF, well, you will have your real and reactive nodal power balance. Of course, it has to be AC. You will set your voltage angles to 0 in the reference bus. Your typically will be your distribution transformer, or if it's a low voltage network, it will be your primary sub. In a medium voltage network, you will define your voltage constraint, your thermal limits, and you will control distribution resources and or network elements, right? So in operation, the distribution networks are inherently unbalanced, all right? So we cannot really do things as a single phase, all right? And this is why there's a block where we're going to discuss three-phase stuff. Single phase or balance is great, but it will have limitations the moment that you want to really go into more detailed studies. In terms of planning, then you have also the aspect that these distributed resources and demand, they are variable, right? People call it intermittent. I don't like that, like referring to renewables as intermittent. But it is variable. So therefore, if we are looking at the planning, then you need to consider, the changes of demand and whatever it is, the other resource. It can be generation, it can be the profiles of electric vehicles, can be whatever, all right? So each application, either operation or planning, will have its own challenges. Operation, well, you need to be very precise, so the models need to be very detailed. In planning, you might not need to be that precise, but then the scale is very big because you're looking at multiple periods, perhaps. Okay. Now, for operation, in a little bit more of detail, well, what I'm presenting here is just saying, well, the ACPF needs to consider the three phases, all right? And we're going to go into more details in the block related to three phase. In terms of the objective function, well, it can be many things, for operation perspective. You're going to harvest as much photovoltaics as possible, generation, or the services from batteries, or you want to minimize power losses at a given moment in time, whatever it is that you want to do. But when it comes to DER and the network, that's where you really need to define things carefully. So you have to define the non-controllable DER. There might be the controllable DER. That's where you extract the settings for. I mean, that's the whole optimization point. You will have controllable network assets, for instance, the LTCs or capacitor banks. And again, that's where you want the settings for. You will have non-controllable network assets as well. And there are many other considerations that you can add. And this is where it gets bigger and bigger and bigger. Can add N-1 security constraints, for instance, fault level constraints. You can have power factors as constraints as well, or as part of being controllable. Curtailment as a constraint. You don't want to curtail too much, for instance. You can use dynamic line ratings. You can do so many things. It's endless. The possibilities. So this is where you start exploring different smart grid schemes. With constraints and controllability. And when will you apply the operational sort of version of an OPF is when a problem occurs. For instance, you are sensing the problems with your monitors every minute, and then if a problem occurs, you do the OPF, and then you calculate the settings, or you do it every control cycle. Control cycle can be, again, a number of seconds or a number of minutes, and then you do it again and again and again. There are a couple of questions here. Sorry, I got carried away with these things. Hosting capacity calculated considering existing generation, and then calculate the capacity to be added additional generation in future. Can we hosting capacity is possible to calculate dynamic envelope for DER? Hosting capacity is for planning. All right. I have heard many people that mix hosting capacity for operational purposes. That's wrong. All right. Hosting capacity is to know how much we can do. And then therefore the nature of it is planning. Dynamic operating envelopes, that's something that we're going to discuss in block 4. But if the question is, can we use OPF for operating envelopes? Yes, absolutely. They're very related because the formulation is very similar, of course, but it's appropriate to use the terms in their own context. Hosting capacity is planning, right? For operation, we're talking about settings, and the operating envelopes are settings. Okay. Sarah, you have another question. What are good international standards for on-load changers? It's not that there are standards for on-load changers. Sarah, really, each company decides how to use, how to control them in the best way possible. It's really not about the standards. The standards are really related to the design of on-load changers, to the relays, perhaps the response, but how you use it, how you control it, that cleverness, it's entirely up to each company. There's nothing there. that tells you this is how you do it. There's a question for Edwin. Active control of DR refers to DERMS. Well, yeah, I mean, that DERMS is another term that is being used a lot. I guess that the Americans started using. I remember many years ago was the California ISO, in a California ISO presentation in a general meeting of PS. They were using this. DERMS is distributed energy resources management systems. Yeah, you can say that the active control of DR will be embedded in DERMS as a platform, because at the end of the day, well, you have your SCADA, you have your distribution management system, you have your DER management system, and these are just little blocks in a full, platform of control and management of your distribution network. But yes, active control can refer to DERMS. That's correct. All right, moving on here, and I'm very aware of the time, so I'm talking too much. I hope you're enjoying it. So I might have to do the break, and then we continue with block 1 in the part of block 2, and then I need to speed up certain things, guys. All right. Now, in terms of planning, now this is what I was referring to. Now it's embedding operation into planning. So formulation-wise, relatively similar. Now here I'm mentioning the 3-phase, of course, but in reality, doing planning with 3-phase is a very difficult task. So I'm just putting this slide as the ideal situation. So I mean, if on top of that, you have to do it in a multi-period way. All right. So catering for whatever it is, years, months or whatever it is, well, it's a massive problem. So therefore, that's why in planning, you're going to see when OPF is used, the balance sort of modeling, all right? And that's adequate as well, because at the end of the day, why do you need to be so precise for planning? Planning means that it's not going to happen tomorrow. It might happen in years. So it's an indicative value. If it is an indicative value, you don't need to be that precise when it comes to, the nature of the unbalance, what is happening in what phase with other phase. So we need to find those trade-offs, according to the application. When it comes to operation, we need to be bloody precise, all right? When it comes to planning, we can have a compromise, so we can actually have a much larger problem and cater for these horizons can be quite extensive. But apart from, the horizon, the fact that it's multi-period, well, I mean, it's very similar, as a formulation, really. But the application is important to understand and the corresponding implications of the application. All right, but to do this well, all right, so I will just use just a few minutes to get into this, and then we will make a break, and I'm happy to answer some other questions. To do this well, all right, so meaning OPF, similar to doing just a power flow, we need proper models, guys. And this is where it gets tricky, all right? Distribution networks, all right, and when you put distributed energy sources in them, we'll have different challenges that we need to cater for, all right? So voltage is a locational effect, all right? So therefore, the network models, the impedances need to be, I would say, pretty decent, okay? I wouldn't say accurate, because it's very, very difficult to have 100% accuracy, all right? Because what you get is, the values from the manufacturer. Well, everyone believes that this is impedance, and then suddenly there have been some changes because no one measured exactly what was happening there in the ground, and perhaps they use another conductor than they say that in the database. So you will always have errors, but still, if it is pretty decent, that's good enough. When we talk about residential distributed resources, well, you need to model the part of the network is connected to it. So it means that we need to connect to model the low voltage part as well. The medium voltage is not enough. Aggregating things to the transformer is just not good enough. Unbalance matters, all right? So the effects of one voltage on the other, or one phase on the other, can be significant, and therefore we need to capture that, all right? We have the fact that demand and DR, they need to be observable and understood, and that requires a lot of data, and that's not easy at all. And well, of course, the network has also a lot of flexible assets, and then they are controlling things as well, like the OLTCs. You have capacitor banks, we have voltage regulators, they are doing their little controls. So that needs to be captured as well, and that adds to complexity. So we need to capture the physics of the medium voltage and low voltage network. This is very, very important. However, in practice, unfortunately, around the world, we do not have complete data sets and models. Distribution networks, of course, they run their business. They have models of the medium voltage. They have adequate models. They try to validate them. They're doing their job, of course. But this hasn't been really extended significantly in most parts of the world to the connection point of your end customers, particularly residential customers, okay? And that brings a lot of challenges as well. Even the medium voltage model, sometimes, there might be some challenges there with data. I mean, it's not available necessarily, that you have smart meter data all over the world, so therefore, your models of demand of whatever is happening there after the transformers, the distribution transformers might not be complete. So there are a lot of challenges, but the companies are doing their best to really improve things. So because of the time, guys, I'm going to stop here. I'm going to continue after a little break that we can have, some 5 minutes. So let me just stop here. Thank you very much. There's no other, well, there's some questions. Let me just answer these questions and then going to stop the recording. There was a rule for the air management. Thanks for that, Sarah, for sharing that. The California rule. And then Krishna, if we use linear three-phase OPF models for planning, how much % accuracy in voltage can be below the actual nonlinear voltages? Well, I don't understand, Krishna, your question, because if you're saying a linearized three-phase OPF, the whole point of, as you hopefully you attended the lecture from Stephen the last 2 days, the whole point of doing relaxations of the OPF is not just making it less accurate so it can be solvable. It has to be accurate as well, all right? So we are not losing, well, we're losing a little bit of accuracy, but it's not massive, all right? And with that, we are actually making it solvable as well. So therefore, the accuracy needs to be tested, all right? And actually in the third block today, we're gonna discuss accuracy as well. And good relaxations, good convexifications, they will end up with pretty good results. Well, not perfect, but definitely pretty good. So we will discuss this a little bit later today. Glover has another question. Explain how to differentiate non-controllable or controllable resources as it is in the course of the grids. So Glover, what I mean is here, for instance, let's suppose that you are controlling a solar PV farm, all right? That's the only thing that you're controlling your network. But this is a solar PV farm that you are controlling because it is being installed in the next few months. So you're creating all the design of how to control, you're measuring whatever point that is important, whatever. But 5 years ago, there's already a wind farm that has been installed and you cannot control it because you cannot put controls back to something that already has been invested, all right? You cannot retrofit. I mean, you can, but normally you will have contracts and things. So you cannot do. So that's what I mean. So you already have technologies that are there, are doing their own things, are non-controllable by your new system, your new DERMS, for instance, your new smart grid. It will not be because of contracts. Unfortunately, that's the reality of the world. Whatever we decide today, it will be fixed for those elements, those participants. And then when we come with something new, it will be applicable to the new installation. So therefore, that's what I mean. So at some moment in time, you will have the non-controllable DER and the controllable DER, and then you will have only to control those that are controllable because the non-controllable are already there. And this is already happening because right now, as I'm saying, 1 in 4 houses in Australia has photovoltaics. Yes, there are projects here, and we're trying to come up with these operating envelopes that I'm going to discuss later today, but you are not going to apply these operating envelopes or other export limits, active control, whatever, on houses that are already invested in their photovoltaics. You're not going to touch them. They installed their technologies with a given set of regulations and requirements for the distribution company. You cannot change that, all right? So the reality is that we will have to model a mix of technologies, some of which will be controllable, some of which will not. So that's what I mean. All right, and with that, I answered those questions, and I will make a break. Thank you very much, and I stop the recording right now.